What if the most terrifying monster from our ancient myths was not a fiction? What if it was real, patiently waiting for us in the silent darkness of the cosmos, a predator not of flesh and bone, but of space-time itself? For generations, we told stories of beasts that lurk in the deepest shadows, creatures that devour light and hope from which there is no escape. We imagined them as dragons, as krakens, as voids at the edge of the map. But we never truly conceived of the reality, an object so profoundly strange, so fundamentally violent, that its very existence seems to mock our understanding of the universe. It is a place where physics collapses into an impossible point of infinite density. A prison from which nothing, not even light, the fastest thing in creation, can ever break free. A gravitational ghost haunting the star fields, detectable only by the carnage it leaves in its wake. For a century, this cosmic phantom was little more than a whisper in the equations, a mathematical nightmare that tormented the greatest minds of science. It was a theory, a terrifying possibility, but it remained stubbornly, maddeningly invisible. You cannot photograph a shadow in a void. You cannot capture an image of pure absence. To see one would require a miracle of ingenuity, a telescope the size of a planet. It would demand that we unite the globe in a singular, audacious quest to accomplish something that bordered on the impossible, to stare into the abyss, and for the very first time to see the monster staring back. This is the story of that quest. The story of a celestial dragon 66 million light-years from home, and the relentless human drive to hunt it down, to corner it, and to capture its portrait, the first direct evidence of a black hole. It is the story of how we, a curious species on a small blue world, finally made the invisible visible, and in doing so proved that one of our own, Albert Einstein, had understood the deepest secrets of the cosmos all along. Our journey begins not in the cold expanse of space, but within the mind of a single man, a mind that would remap our entire perception of reality. In 1915, Albert Einstein presented his theory of general relativity to the world, and it was a masterpiece, a symphony of logic and mathematics. He revealed that space and time were not a static stage for the universe to perform upon, but a dynamic, interwoven fabric, space-time, that could be bent, warped, and curved by mass and energy. Planets orbiting the sun were not being pulled by an unseen force. They were rolling along grooves carved into this cosmic fabric by the sun's immense weight. It was an idea of breathtaking elegance and power, explaining the motion of stars and galaxies with unparalleled precision. But buried deep within the architecture of his own magnificent equations, a demon was stirring. Einstein's theory was so powerful, so complete, that it predicted things even he wasn't ready to accept. Just a few months after his theory was published, a German astronomer named Karl Schwarzschild, serving on the Russian front during the First World War, found a solution. He was calculating the gravitational field of a single non-rotating spherical star, and his mathematics revealed something deeply unsettling, a breaking point in reality. Schwarzschild discovered that if you could compress enough mass into a small enough volume, the curvature of space-time would become infinite. It would tear a hole in the very fabric of the universe. At a certain boundary, what we now call the event horizon, gravity would become so absolute, so completely overpowering, that the escape velocity would exceed the speed of light. It was a one-way cosmic door. Anything that crossed this threshold, a planet, a star, a particle of light, would be lost forever, crushed into a singularity, a point of zero volume and infinite density. The idea was grotesque. It was an absurdity. Einstein himself found the concept abhorrent, a mathematical blemish on his beautiful theory. He believed, and certainly hoped, that in the real universe some unknown physical principle, some law of nature, would prevent such a monstrous object from ever forming. For decades, the scientific community agreed. These dark stars, or frozen stars as they were sometimes called, were relegated to the realm of theoretical curiosities, mathematical oddities that surely had no place in the physical cosmos. They were a ghost in the machine of relativity, a phantom that most physicists chose to ignore. The universe, they felt, must be more sensible than that. But the universe is under no obligation to make sense to us. And as our eyes on the sky grew ever more powerful, throughout the 20th century we began to see things that defied all conventional explanation. We began to find its footprints. The hunt for the invisible monster had begun, not with a deliberate search, but with a series of baffling astronomical puzzles that pointed to something dark and massive, hiding in plain sight, veiled by its own perfect gravitational shroud. In the 1960s, astronomers turned their newly invented radio telescopes to the heavens, and they found bizarre points of light more luminous than entire galaxies flickering at the very edge of the observable universe. They were called quasi-stellar radio sources, or quasars. These objects were pouring out more energy than 1 trillion suns combined from a region of space no larger than our own solar system. What celestial engine could possibly generate such cataclysmic power? The only plausible explanation was matter being superheated to millions of degrees as it was torn apart in a violent, swirling vortex, a maelstrom of destruction spiraling into an object of unimaginable mass and gravity. It was the death scream of stars, a final brilliant flash before being consumed. The evidence was circumstantial, but it was compelling. Then in 1971, we found a suspect much closer to home. In the constellation, Cygnus astronomers detected a powerful erratic source of X-rays, Cygnus X1. They tracked it to a blue supergiant star, a massive brilliant sun. But this star was not alone. It was wobbling, dancing in orbit with an unseen partner. By measuring the star's orbital dance, we could calculate the mass of its invisible companion. The result was staggering. The dark partner weighed at least 15 times the mass of our Sun, yet it was completely, utterly black. No known object, not a white dwarf or a neutron star, could pack that much mass into such a small dark space. The only candidate left on the list was the one physicists had dreaded for half a century. We were watching a star being slowly cannibalized by a black hole. The evidence was mounting, building an airtight case for the existence of these gravitational phantoms. The most dramatic clues, however, were found right in our own cosmic backyard, at the very heart of our galaxy, the Milky Way. For decades, we observed the stars at the galactic center, a region shrouded in gas and dust. Using infrared telescopes that could pierce through the veil, we watched a small cluster of stars moving at truly mind-boggling speeds. They were whipping around a single empty point in space like planets, in a frantic, chaotic orbit. One star named S2 completes its orbit in just 16 years, reaching speeds of over 25 million kilometers per hour as it makes its closest approach. There was no other explanation. These stars were tethered by the immense gravity of a supermassive black hole, a colossal beast 4 million times the mass of our Sun lurking silently at the center of our galaxy. We had proven beyond any reasonable doubt that they were real. We saw their shadows cast upon the cosmos. We saw the wreckage they left behind the tortured stars caught in their grip. We heard the gravitational echoes of their violent collisions rippling across space-time itself. But we had never seen one. And that is a profound distinction. Seeing the effect is not the same as seeing the cause. It's like trying to understand a fire by studying only the smoke from a great distance. To truly confirm our theories, to test the absolute limits of Einstein's relativity, we had to go beyond the circumstantial evidence. We had to see the thing itself. But how do you take a picture of something that consumes light? The very concept seems like a contradiction in terms of fool's errand. A black hole by its very nature has no surface to photograph. It is a rupture in reality, an object defined by what isn't there. The challenge is compounded by a mind-shattering problem of scale. Even the supermassive black hole at the center of our own galaxy, Sagittarius A, is an impossibly small target. Though it contains the mass of 4 million suns, its event horizon, the point of no return, would fit comfortably inside the orbit of Mercury. Imagine trying to photograph a single grapefruit sitting on the surface of the Moon, but using a telescope located here on Earth. That is the scale of the challenge we faced. No single telescope could ever achieve such a feat. The laws of optics dictate that to get a sharper image to resolve smaller details, you need a bigger lens, a larger dish. To see the event horizon of a black hole, we would require a telescope not meters wide, but thousands of kilometers in diameter. We would need a telescope the size of the Earth. For any sane engineer or astronomer, the dream would have ended there. It was impossible, a dead end. But human curiosity is not always sane. And in science, the word impossible is often just a temporary obstacle, an invitation for a more radical idea. A new kind of vision was needed. What if instead of building one colossal telescope, you could create a virtual one? What if you could link together radio telescopes scattered all across the globe, from the volcanic peaks of Hawaii to the frozen plains of Antarctica, from the mountains of Spain to the deserts of Chile? What if you could synchronize them with atomic clocks so precise they would lose only 1 second every 10 million years, making them all function as tiny individual pieces of a single planet-sized mirror? If you could capture the faint radio waves from a black hole's edge at the exact same moment in multiple locations, and then combine that data using supercomputers, you could in theory synthesize an image with the same astonishing resolution as a telescope the size of the Earth. This was the breathtakingly ambitious dream behind the Event Horizon Telescope, or EHT. It was a global scientific conspiracy, a collaboration of hundreds of scientists from dozens of countries, all united by a single, ludicrously bold objective. They were building a planetary camera to photograph the unseeable, but which black hole would they target? Our own galaxy's black hole was a candidate, but it was notoriously fickle, its light flickering and changing on a timescale of minutes, making it a blurry, difficult subject. They needed a bigger, more stable monster, a true titan. And they knew just where to find one. Their gaze turned to the constellation Virgo, 55 million light-years away. There resides a galaxy that dwarfs our own, a cosmic kingdom unlike any other. It is Messier 87, or M87. M87 is not a beautiful swirling spiral like our Milky Way. It is an elliptical galaxy, a vast featureless incandescent blob of stars. It is old ancient, composed of nearly 2 trillion suns, most of them far older than our own. It is a galactic tyrant, having grown to its colossal size by devouring smaller galaxies over billions of years. It is a gravitational behemoth, a city of old golden stars, and from the very heart of this immense galaxy, something extraordinary is happening. A luminous spear of energy, a celestial blowtorch 5,000 light-years long, is being ejected from its core at nearly the speed of the light. This relativistic jet is one of the most energetic and mysterious phenomena in the known universe. For decades, we knew that only one engine could be powerful enough to launch such a cosmic weapon. At the centre of M87, there had to be a black hole of truly epic proportions. This was the target. 87 supermassive black hole, more than 1,000 times larger than the one in our own galaxy. It is a gravitational leviathan weighing 6.5 billion times the mass of our Sun. Its event horizon is so vast it could swallow our entire solar system whole, its shadow stretching for light days across space. Its sheer size made it the perfect subject. It was a stable, steady giant, a celestial dragon sitting for its portrait. If the Event Horizon Telescope could work, if this global array of synchronized dishes could achieve the impossible, this was the place we would see it. This was our laboratory. The stakes were higher than simply taking an astronomical photograph. What the EHT was attempting to see was the very edge of reality. General relativity predicted exactly what the shadow of a black hole should look like. It would not be a simple black circle. The black hole's immense gravity would warp the space-time around it so severely that it would act as a powerful cosmic lens. Light from the hot glowing gas swirling just outside the event horizon, the accretion disk would be bent and twisted into a perfect glowing ring of fire, a halo of light encircling a central darkness. The size and shape of that shadow, the precise curve of that luminous ring, would be a direct, incontrovertible test of Einstein's theory in the most extreme environment imaginable. If the image matched the predictions, it would be the ultimate confirmation of his century-old vision. It would be a triumph cementing his legacy as the architect of our cosmic understanding. But if the shadow looked different, if it was the wrong size, the wrong shape, or not there at all, it would mean our understanding of gravity, the most fundamental force of the universe, was broken. It could signal the beginning of a new physics, a revolution in our comprehension of the cosmos. After decades of theory of chasing ghosts in equations and hunting for circumstantial clues, the moment of truth was at hand. An entire planet had been transformed into a single scientific instrument, its gaze fixed on a single point of darkness in a distant galaxy. All for the chance to answer a simple yet profound question: what does the edge of forever look like? The data was collected, the hard drives were flown across the world, and the most complex computational puzzle in the history of astronomy began. The world held its breath waiting for an image that many believed we would never see. An image of the void, an image of the end of time, an image of the monster in the dark. What happens when the most fundamental force in the universe, the architect of galaxies and the anchor of worlds, turns against itself? What happens when gravity, the gentle curve in space-time that holds you to your chair, begins to pull with such ferocity that it tears the very fabric of reality? This isn't a question of science fiction. It is the unnerving, paradoxical question that haunted the mind of Albert Einstein himself, born from the elegant mathematics of his own masterpiece, the general theory of relativity. In 1915, he had given humanity a new cosmos, a dynamic four-dimensional universe, where space and time were woven together, where planets followed the contours of space-time bent by the mass of their star. It was a universe of sublime cosmic clockwork. But within the gears of his own equations, a ghost was stirring. A prediction so bizarre, so violent, so contrary to the orderly universe, he envisioned that he refused to believe it. His theory described an object so dense that its gravitational pull would become infinite at its centre, a point he called a singularity. Around this point of infinite density, space would curve so steeply that it would effectively close in on itself, creating a one-way cosmic membrane from which nothing, not even light, could escape. Einstein called it an aberration. He was convinced that in the real universe, some yet unknown physical principle, some natural barrier must prevent such a monstrosity from ever forming. Nature, he believed, would not permit such a catastrophic failure of its own laws. Yet the mathematics was relentless, a cold and unforgiving logic that paid no heed to the philosophical discomfort of its creator. As the world plunged into the chaos of the First World War, a German physicist and astronomer named Karl Schwarzschild found himself on the Russian front calculating artillery trajectories. In the lulls between battles, he turned his mind to the pristine beauty of Einstein's new equations. And there, amidst the mud and horror of the trenches, he became the first person to find an exact solution. He discovered a terrifyingly simple answer to what the universe would look like around a single, non-rotating sphere of mass. His calculations revealed a critical boundary, a finite distance from the centre of this object now known as the Schwarzschild radius. If you could compress any object, be it a star or a planet, down to a size smaller than this radius, its gravity would become so overwhelming that it would collapse forever, sealing itself off from the rest of the universe. This was no longer a vague mathematical phantom. It was a number, a precise threshold for oblivion. Schwarzschild had drawn the map to a place that shouldn't exist. He had mathematically defined the point of no return. Justusn. Cross this invisible border and all paths, every possible trajectory through space-time would lead inexorably to the central singularity. There is no turning back, no engine powerful enough, no velocity great enough could ever pull you free. You're not simply falling in space. Space itself is falling, dragging you along with it into an infinite abyss. It was a gravitational wound in the cosmos, a place where physics as we understood it simply ceased to function. The idea was so radical that for decades it remained little more than a mathematical curiosity, a fringe concept debated by theoretical physicists in quiet university halls. For a generation, these objects were known by cumbersome names like gravitationally completely collapsed objects, or frozen stars, a term that hinted at the bizarre way time itself would seem to grind to a halt at the boundary for any distant observer. The concept lacked a name that could capture its profound and terrifying nature, a name that could launch it from the esoteric pages of physics journals into the public imagination. That name would arrive in the 1960s, coined by the brilliant and flamboyant physicist John Archibald Wheeler. He sought a word that was simple, powerful, and evocative. He found it in two words: black hole. The name was perfect. It was a declaration. It transformed a complex mathematical solution into a tangible monster lurking in the cosmic dark. A black hole, a void from which no information could escape, a region of pure darkness, defined by its insatiable appetite. Wheeler gave the phantom a name, and in doing so, he gave scientists a target. The hunt was on. But how do you hunt for a creature that is by its very definition perfectly black, utterly invisible? You don't look for the creature itself, You look for the signs of its passing. You search for its victims. In the early 1960s, astronomers were mystified by the discovery of impossibly bright star-like points of light in the distant universe. They were named quasi-stellar radio sources, or quasars. These were no ordinary stars. A single quasar could outshine its entire host galaxy, a feat equivalent to a single light bulb generating more light than all the cities on Earth combined. What conceivable engine could generate such an astonishing amount of energy? The light from these quasars varied over periods of weeks or even days, a critical clue that told astronomers the source of this immense power had to be incredibly small, no larger than our own solar system. A galaxy-wide firestorm was being generated in a cosmic teacup. There was only one candidate for a power source that was both compact enough and powerful enough to explain the quasar phenomenon. It was the gravitational death spiral of matter falling into a supermassive black hole. The light we were seeing wasn't coming from inside the black hole itself, for that is impossible. Instead, it was the final brilliant scream of matter being torn apart just outside the point of no return. As gas, dust, and entire stars are drawn in by the immense gravity, they don't fall straight in. They form a vast swirling disk of material called an accretion disk, a celestial whirlpool accelerating to near the speed of light. The friction within this disk, the sheer violence of matter being shredded at a subatomic level, heats it to millions of degrees, turning it into a blindingly luminous plasma. The accretion disk becomes a celestial blowtorch, the most efficient engine in the known universe, converting the mass of infalling matter into pure energy with an efficiency that dwarfs nuclear fusion. Quasars were our first tantalizing indirect glimpse. They were the lighthouses of the cosmic ocean, signaling the presence of gravitational reefs of unimaginable danger and power. They proved that not only did black holes likely exist, but that they were titanic engines of creation and destruction, actively shaping the evolution of galaxies across cosmic history. This evidence, however, was distant, found in the far reaches of the ancient universe. To truly confirm their existence to silence the remaining skeptics, astronomers needed to find one closer to home to see its influence, not on a galactic scale, but on individual stars. The search turned inward toward the very heart of our own galaxy, the Milky Way. Deep within the constellation of Sagittarius lies the galactic center, a region shrouded from our view in visible light by thick clouds of interstellar dust and gas. But using infrared telescopes which can pierce through this cosmic veil, astronomers began a patient decades-long stakeout. Two independent teams, one led by Reinhard Genzel in Germany, and another by Andrea Ghez in the United States, began meticulously tracking the movements of a small cluster of stars orbiting an unseen point right at the galaxy's core. For years, then decades, they watched. What they saw was breathtaking. These were not the slow, stately orbits of planets in our solar system. These were stars, massive suns, whipping around this invisible point at incredible speeds. One star designated SCS-2 completes its orbit in just 16 years, reaching speeds of over 8,000 kilometers per second as it makes its closest approach. It was like watching a celestial dance where one of the partners was a ghost. The stars were gravitational ballerinas, their frantic elliptical paths sketching the precise location and mass of their unseen partner. By applying Kepler's laws of planetary motion, the same laws that govern the Earth's orbit around the Sun, the astronomers could calculate the mass of the object these stars were orbiting. The result was staggering. All of these stars were bound to a single dark object that contained the mass of 4 million suns, all compressed into a region of space smaller than the orbit of Mercury. There was nothing in the known astronomical zoo that could be that massive, that compact, and that dark. It couldn't be a dense star cluster as the individual stars would have been visible. It couldn't be a cloud of exotic matter as it would have collapsed or dispersed. Every alternative explanation failed. The only thing that fit the data, the only object that could command such gravitational authority, while remaining completely invisible, was a supermassive black hole. This was the smoking gun. Here in our own galactic backyard was the proof. Genzel and Ghez's meticulous Nobel Prize-winning work transformed the black hole from a theoretical necessity into a confirmed reality. We now knew with near certainty that we shared our galaxy with a sleeping monster. Yet even with this overwhelming indirect evidence, the ultimate prize remained elusive, a direct image. To see one with our own eyes. But this presents a challenge so profound it borders on the absurd. How do you photograph an object whose defining characteristic is that it consumes light itself? You can't. The black hole itself, the region inside the point of no return, will forever remain hidden from us. But the theory that predicted its existence also offered a tantalizing possibility, a loophole. While the interior is forever dark, the boundary, the event horizon, should cast a shadow. Imagine the black hole surrounded by its glowing superheated accretion disk. This disk of plasma acts as a brilliant backlight. According to general relativity, the black hole's immense gravity will warp space-time around it so severely that it acts like a lens, a gravitational magnifying glass. This lensing effect would bend the light from the plasma behind the black hole, creating a bright ring of light around a central dark patch. That dark patch is the black hole shadow. It is the direct visual footprint of the event horizon, a silhouette of oblivion cast against the fires of the abyss. Seeing this shadow, this precise ring of light, would be the final definitive proof of Einstein's theory, in the most extreme environment the universe has to offer. It would be like seeing the face of gravity itself. The problem, however, is one of scale. Even the largest supermassive black holes are in astronomical terms shockingly small. The shadow cast by the 4 million solar mass black hole at the centre of our Milky Way Sagittarius A would appear in our sky to be about the same size as a grapefruit sitting on the surface of the moon. To resolve an image that tiny requires a telescope with an angular resolution thousands of times better than the Hubble Space Telescope. No single-dish telescope on Earth or even in orbit could ever be built large enough to achieve this feat. The laws of optics dictate that to get higher resolution you need a bigger primary mirror, a bigger eye on the universe. To see the shadow of a black hole, you would need a telescope with a mirror the size of a city or a continent. The dream of seeing a black hole seemed destined to remain just that, a dream, an impossible goal. But what if you could build a telescope not out of a single piece of glass, but out of the entire planet? This was the audacious, almost ludicrously ambitious idea behind the Event Horizon Telescope, or EHT. It proposed to link radio telescopes across the globe from the mountains of Hawaii to the deserts of Chile, from the plains of Spain to the ice of the South Pole. By using a technique called very long baseline interferometry, these disparate observatories could be synchronized with atomic clocks of unimaginable precision. They would all observe the same target at the exact same time, effectively working together as a single virtual telescope dish with a diameter nearly as wide as the Earth itself. It was a technological feat of staggering complexity, a global collaboration requiring the seamless coordination of hundreds of scientists and engineers across dozens of countries. For the first time in history, humanity was building an eye large enough to resolve a grapefruit on the moon. We were building an eye powerful enough to see a shadow at the edge of reality. But which shadow should it look for? While our own galaxy's black hole, Sagittarius A, is close, it is relatively quiescent, and its view is cluttered by the intervening gas and dust of the Milky Way's disk. The EHT needed a target that was bigger, bolder, and more active. They needed a true monster. They found it in the constellation Virgo, 55 million light-years from Earth, at the heart of the colossal elliptical galaxy Messier 87. There resides a black hole of almost incomprehensible scale, a true cosmic titan. M87 is not 4 million times the mass of our Sun. It is over 6.5 billion times the mass of our Sun. It is one of the most massive black holes known to exist. This sheer size is its first great advantage. Its gargantuan mass means its Schwarzschild radius, and therefore its shadow is enormous, more than 1,000 times larger than the one in our own galaxy, making it a far easier target to resolve despite its greater distance. Secondly, its location is ideal. M87 lies far outside the plane of the Milky Way, giving us a clear, unobstructed line of sight free from the foreground clutter that plagues observations of our own galactic centre. But the most compelling feature of M87, the feature that made it the perfect protagonist for this story, is that it is not a sleeping giant. It is a monster that is actively feeding, and as it feeds, it unleashes one of the most spectacular and violent phenomena in the universe, a relativistic jet. From its core, M87 is spewing a colossal focused beam of energized particles, a celestial fire hose travelling at over 99% the speed of light. This jet, visible even to amateur telescopes, stretches for 5,000 light-years into intergalactic space. It is the definitive signature, the cosmic smoking gun that proves a powerful engine is at work. The existence of this jet guarantees that M87 is surrounded by a massive, brilliantly glowing accretion disk, the perfect backlight needed to cast the all-important shadow. It was the ideal candidate. The stage was set. The global eye was about to open. To see a thing is to catch the light that has touched it. But the object of our obsession, the supermassive heart of Messier 87, was so distant, its apparent size so infinitesimally small, that no single telescope dish on Earth, no matter how vast, could ever hope to resolve it. It was the equivalent of trying to spot a single orange sitting on the surface of the moon from your backyard. The laws of physics, specifically the diffraction limit, seem to have drawn a final uncrossable line. To achieve that resolution, we would need a mirror, a lens, a dish stretching not hundreds of meters, but thousands of kilometers across. We would need a telescope the size of a planet. And since building such a monument is the stuff of science fiction, an entirely different, almost audacious idea began to take hold in the minds of astronomers. An idea that didn't require steel and concrete, but something far more ethereal, perfect timing and global trust. What if instead of building one impossible telescope, we could fake one? What if we could teach the Earth itself to see? This is the revolutionary principle behind a technique with a deceptively simple name: Very Long Baseline Interferometry, or VLBI. It's a trick and act of cosmic ventriloquism. Imagine standing by a still pond. If you drop two pebbles in, the ripples from each will spread out and interact, creating a complex pattern of crests and troughs. By studying that interference pattern, you could work backward and deduce the precise location of the two pebbles without ever seeing them directly. VLBI does the exact same thing, but the pond is the fabric of space-time. The pebbles are distant radio telescopes and the ripples are the ancient waves of light that have travelled 55 million years from the edge of M87's abyss. The plan was to use not two, but an entire array of the world's most sensitive radio observatories scattered across the globe, from the bone-dry Atacama Desert in Chile to the volcanic peaks of Hawaii, from the mountains of Arizona to the frozen plains of Antarctica. Each telescope in this global network would stare at M87 thirst at the exact same moment, listening intently to the faint radio whisper emanating from its chaotic surroundings. They would each record a piece of the story, a single thread in a vast cosmic tapestry, but a single thread tells you nothing. The magic, the miracle of VLBI happens when you bring all those threads together. By combining the signals from these disparate locations, we could synthesize a virtual telescope, a synthetic aperture, with a diameter not of a single dish, but of the largest distance between any two telescopes in the array. We were creating a ghost telescope, an instrument whose mirror was the very curvature of our world. This endeavour was christened the Event Horizon Telescope, the EHT, and it represented one of the most complex, most ambitious, and most profoundly international scientific collaborations ever attempted by humankind. It wasn't just about pointing dishes in the right direction. It was a challenge of planetary choreography, a symphony of precision engineering that pushed our technology to its absolute limit. The first and most critical hurdle was time itself. For the interference trick to work, the light waves, arriving at each observatory, had to be time-stamped with a precision that beggars belief. If the timing was off by even a nanosecond, a billionth of a second, the delicate wave patterns would be smeared into meaningless noise. The entire project would fail. We needed a clock, a metronome that was more stable than the rotation of the Earth, more reliable than the rising of the sun. We needed an atomic clock. At each of the EHT sites from the South Pole telescope, enduring temperatures that would freeze steel to the sub-millimeter array, perched above the clouds on Mauna Kea, a hydrogen maester atomic clock was installed. These are not timekeepers in the conventional sense. They are physics experiments harnessing the quantum leap of electrons inside a hydrogen atom. An atom of hydrogen, when energized, will always emit radiation at a precise unchanging frequency, 1,420,45,751.768 cycles per second. It is a heartbeat of pure physics, a standard given to us by the universe itself. These clocks are so fantastically accurate that if you had started one ticking at the Big Bang, it would only be off by a few seconds today. This extraordinary precision allowed every single wavefront from M87 captured in Chile to be perfectly aligned with its counterpart captured fractions of a second later in Spain. It was this shared hyper-accurate sense of now that held the entire virtual telescope together, allowing the light from a dozen different perspectives to be woven into a single coherent image. With timing solved, the next challenge was just as monumental: data. The torrent of information pouring from these telescopes was simply staggering. Each observatory was capturing radio waves at such a high frequency, and with such sensitivity that it generated a flood of data far too vast to be sent over the internet. We're not talking about gigabytes or even terabytes. We're talking about petabytes, thousands of terabytes from a single observing run. The total data volume was so immense that the fastest way to move it from a remote mountaintop in Mexico to a central processing facility in Massachusetts was not through fiber optic cables, but on a commercial jet. Hundreds of specialized helium-filled hard drives were carefully packed into crates and flown across the world. This physical journey of the data became a crucial part of the experiment itself. It was a digital fossil, the raw, unprocessed echo of a black hole, carefully transported like a priceless artifact. A single lost or corrupted drive could create a hole in our virtual mirror, a blind spot in our planet-sized eye, potentially jeopardizing the entire effort. And so, for a few weeks, the most valuable cargo flying through our skies wasn't gold or diamonds, but the captured ghost of a distant monster. This global network of telescopes synchronized by atomic clocks and bound together by petabytes of data was our instrument. It was the most powerful radio interferometer ever conceived, an engineering marvel born from a simple, elegant idea. But it was still just an instrument. Like any telescope, it needed to be aimed at its target. And to understand what we were about to see, to interpret the image that might emerge from this global conspiracy of science, we had to turn not to engineers but to a theorist who had laid the groundwork a century before. We had to return to Albert Einstein. His theory of general relativity didn't just predict the existence of black holes, it made startlingly precise predictions about what one should look like. If you could somehow get close enough, if you had a telescope powerful enough, what would you actually see? You wouldn't see the event horizon itself, for the horizon is the ultimate boundary from which no light can escape. It is by its very nature perfectly invisible. What you would see is something even more profound: a shadow. The black hole's immense gravity acts as the most powerful lens in the universe, bending and distorting the path of light from anything behind it. Light rays that would have otherwise flown safely past are captured, their paths bent inexorably down into the abyss. This creates a dark region in the sky, a void carved from the background light known as the black hole shadow. Einstein's mathematics predicted that this shadow would be a near-perfect circle, a cosmic silhouette cast by the black hole against the glowing backdrop of its surroundings, and crucially, the theory predicted its exact size. The shadow would not be the size of the event horizon, but roughly 2.5 times larger. This amplification is a direct consequence of the warped geometry of space-time, a pure manifestation of gravity's power to steer light. Observing the size and shape of this shadow would therefore be more than just taking a picture. It would be a direct, unambiguous test of general relativity in the most extreme environment we have ever found. Any deviation from that perfect circle, any change in that predicted size, would be a crack in the foundation of our century-old understanding of gravity. It would be a signpost pointing toward a new undiscovered physics, but a black hole isn't a neat, tidy object sitting in an empty void. M87 is a cosmic engine, a ravenous beast surrounded by a swirling vortex of superheated gas and shredded stars, its accretion disk. This disk is a maelstrom of incandescent matter, a celestial inferno where temperatures reach billions of degrees hotter than the core of our sun. Trapped in the black hole's gravitational grip, this plasma orbits at terrifying speeds approaching the speed of light itself. Magnetic fields twisted into impossibly tight coils by the black hole's spin channel, this energy acting like a cosmic particle accelerator and launching the colossal jets we had observed for decades. This glowing chaotic disk is the source of the light that the Event Horizon telescope was built to capture. It is the luminous backdrop against which the black hole's shadow would be cast, and general relativity made another stunning prediction about this disk. Because the matter in it is moving so incredibly fast, the effects of special and general relativity would become obvious and dramatic. The gas swirling towards us would have its light amplified and brightened by a phenomenon called relativistic beaming or Doppler boosting. At the same time, the gas swirling away from us on the other side of the disk would appear fainter. The result, according to the simulations, should be a lopsided ring of light. Not a uniform halo, but a brilliant crescent, a glowing, asymmetrical smile with the dark shadow of the black hole nestled in its centre. This predicted brightness asymmetry was a vital clue. It would be a fingerprint of the extreme physics at play, a direct visual confirmation that we were witnessing matter moving at near-light speeds in a gravitational field of unimaginable strength. Some models went even further, suggesting that the black hole's own spin would drag the very fabric of space-time around with it, an effect called frame dragging. This cosmic gyroscope, the spinning of space-time itself, would subtly alter the shape and position of the bright crescent, giving us a potential way to measure not just the black hole's mass but its rotation. The theoretical groundwork was laid. The predictions were clear. We were not looking for a simple dot. We were searching for two specific intertwined features, both born from Einstein's equations. First, a dark circular shadow, its size dictated by the black hole's mass and the fundamental laws of gravity. And second, surrounding that shadow, a blazing lopsided ring of light, a testament to the violent relativistic dance of matter at the brink of oblivion. The EHT was the instrument designed with unprecedented precision to see exactly these features. It was a machine built to test a theory. For years, supercomputers had run simulations generating thousands of possible images of what M87 might look like through the Earth-sized lens we were building. They fed in different assumptions about the black hole's spin, the temperature of the gas, the orientation of the magnetic fields. And while the details varied, the core prediction remained robust, a shadow inside a ring. A dark heart inside a blaze of glory. The scale of the collaboration was as breathtaking as the science. More than 200 scientists and engineers from over 60 institutions spanning 20 countries and regions had come together. They were a testament to what humanity can achieve when we pool our curiosity and our intellect to pursue a single, seemingly impossible goal. They had overcome political boundaries, language barriers, and logistical nightmares. They had trekked to some of the most remote and inhospitable places on the planet, all to install and operate the components of this extraordinary machine. The telescopes were ready. The atomic clocks were synchronized to within a trillionth of a second. The data recorders were standing by, ready to capture the deluge of information. The theoretical physicists had made their predictions, drawing a clear target on the wall of the cosmos. All the pieces were in place. Now all they needed was for the universe to cooperate. They needed clear skies, not just at one observatory, but simultaneously across the entire planet. They needed every piece of exquisitely complex technology at every single station to work flawlessly at the exact same moment. For a few precious days in April of 2017, this global network of observatories would hold its collective breath and open its planetary eye. The hope was that when the light from Messier 87 finally arrived after its 55 million year journey, humanity would be ready waiting to catch it. We were about to attempt to see the unseeable. The simulations were complete, the theories tested against every known law of physics. On screens in darkened rooms across the world, the shadow of a monster lurked, a perfect void rendered in the cold, clean language of mathematics. But a ghost in the machine is not a discovery. A prediction is not a photograph. To bridge the 55 million light-year chasm separating our world from the heart of galaxy M87, to turn that elegant equation into an observation required something more than computation. It required a celestial alignment not of stars but of humanity itself. It demanded a symphony of steel and silicon played on a planetary scale, with every instrument tuned to a single, impossibly faint cosmic note. The time for theory was over. April 2017 was the moment of truth. The window of opportunity was terrifyingly brief. For only a few precious nights each year, M87 rises in the sky simultaneously, for a network of radio telescopes scattered across the globe from the volcanic peaks of Hawaii to the frozen plateau of Antarctica. This is the only time our planet in its relentless spin can present the correct face to its distant target, allowing the telescopes to work in concert. The Earth itself had to become the lens, and for that to happen, everything had to be perfect. The weather at every single site had to be clear, dry and stable, a meteorological miracle across 4 continents. Every piece of hyper-specialized, often bespoke equipment had to function flawlessly. Hundreds of scientists, engineers and technicians had to move as one. It was an intricate global choreography where a single misstep, a single cloud bank over a Chilean desert, could bring the entire multi-decade effort to a halt. The nerve center of this audacious operation was not a single grand control room, but a distributed network of minds connected by encrypted chat channels and tense video calls. From Cambridge, Massachusetts to Bonn, Germany, project leaders watched the world map their screens glowing with weather satellite data and telemetry from each station. They were conductors of a silent orchestra, trying to bring their global instrument online. The pressure was immense, a palpable weight in every email, every status update. Years of careers, hundreds of millions of dollars in funding, and the dream of a generation of astrophysicists were all balanced on the edge of this fleeting moment. They were attempting to measure a shadow, the apparent size of a donut placed on the surface of the moon, and to do it they had to contend with the chaos of Earth's own atmosphere. Imagine the Atacama Large Millimeter Array ALMA high in the Chilean Andes. Here at 16,000 feet, the air is so thin it feels like another world. 66 pristine dishes, a forest of technology in an alien landscape had to pivot in unison, their gaze locked on a single point in the constellation Virgo. The teams on site, battling altitude sickness and the biting cold of the high desert night, performed their final checks. A single loose cable, a momentary software glitch could render the most powerful radio observatory on Earth blind at the critical instant. The data from ALMA was the linchpin. Its sensitivity was so great that without it, the entire experiment would likely fail. Its success was not guaranteed. The mountain winds, which could whip up without warning, threatened to buffet the dishes, blurring the very signal they sought to capture. Thousands of miles away on the frozen expanse of the Antarctic plateau, another team faced an even more profound isolation. The South Pole Telescope, a stark white sentinel against an endless sweep of ice, was at the very ragged edge of the world. Here the challenge wasn't just wind, but a cold so profound it can shatter steel. At minus 40 degrees Celsius, every human action is a struggle. Every piece of machinery operates at the absolute limit of its endurance. The scientists stationed there for the long polar winter knew that if something broke, there would be no rescue, no spare parts flown in. The continent was locked down by the encroaching winter darkness. They were on their own, the most remote and crucial anchor of this entire planetary telescope. Their observations were vital, providing the longest possible north-south baseline, the very key to achieving the EHT's extraordinary resolution. If the South Pole failed, the virtual lens would have a catastrophic blind spot, and so it went across the globe. In Hawaii, astronomers on Mauna Kea prayed for clear skies, hoping the moisture-laden Pacific air would not cloud their view. In Spain's Sierra Nevada, the IRAM 30-meter telescope swiveled into position, a giant metallic ear pointed toward the heavens. In Arizona and Mexico, each station reported its readiness, a chorus of voices echoing across time zones. The designated observation period was a mere 10 days. Within that slot, they hoped for 5 nights of usable coordinated data. Each night, the go-no-go decision was an agonizing calculus of risk and hope. A project scientist would make the final call staring at weather models that were at best educated guesses. To trigger the observation was to commit immense resources to start the atomic clocks and the data recorders whirring across the planet. To hesitate was to risk losing a perfect night, a night that might not come again for another year. On April 5, 2017, the call was made. Go. Across the planet, a silent command was issued. The great dishes from the deserts to the ice began to move as one. They were no longer individual observatories. For the next several hours, they would function as a single integrated scientific instrument, a telescope the size of a world, its aperture spanning nearly the full diameter of the Earth, their target the invisible point of gravitational fury at the heart of a galaxy, millions of light years away. The experiment had begun. There was nothing to see, no dramatic flash or cosmic event. There was only the quiet, relentless acquisition of data. At each telescope, a specialized piece of equipment, a digital backend, intercepted the faint radio waves collected by the dish. These were not images. They were a torrent of noisy, chaotic signals, the faint whisper of M87's accretion disk, buried in a cacophony of cosmic static and atmospheric interference. To preserve the integrity of this whisper, every signal was time-stamped with mind-boggling precision by a hydrogen Messier atomic clock at each site. These clocks, the unsung heroes of the experiment, are so stable they would lose less than a single second over the course of 10 million years. This perfect synchronization was the secret to the entire endeavour. It was this shared, ultra-precise timeline that would later allow astronomers to align the waves of light from each telescope to effectively stitch them together and create the interference patterns that held the secret of the black hole's shape. Without it, the data would be nothing more than random noise, a meaningless digital scream. The signals were then digitized and funneled into a vast bank of helium-filled hard drives. The sheer volume of information being recorded was staggering, a digital tsunami, unlike anything in the history of astronomy. Each telescope recorded data at a rate of 64 gigabits per second. Over the course of a single night's observation, the network would generate close to a petabyte of data. That's 1 million gigabytes. Enough information to fill thousands of laptops, equivalent to the entire selfie library of 40,000 people over their whole lives, or half of all the written works of humanity from the beginning of recorded history in every language. This data stream was so colossal, so overwhelmingly vast, that it was impossible to transmit over the internet. No network on Earth could handle it. The information had to be physically transported. The most advanced astronomical observation in history relied on the oldest method of data transfer, putting it on a plane. As the observation nights ticked by, some successful, some lost to weather, a mountain of hard drives grew at each site. 5 petabytes in total. A library of cosmic secrets locked away on spinning platters of metal and glass. Crates were carefully packed in Chile and Spain and Arizona. They were loaded onto commercial cargo flights, each one a precious, irreplaceable piece of a planet-sized puzzle. The logistical challenge was immense. Customs forms had to be navigated, shipping manifests triple-checked. A lost crate would be a disaster, a hole punched through their virtual mirror, creating a gap in the data that could corrupt the final image. The teams at the Haystack Observatory in Massachusetts and the Max Planck Institute for Radio Astronomy in Germany waited their supercomputers ready for the coming deluge. These 2 locations would serve as the processing centres, the places where the raw, chaotic signals would be painstakingly compared and combined. But there was one shipment that could not be made. At the South Pole, as the observations concluded, winter had descended in earnest. The last flight out had departed. The continent was now shrouded in 24-hour darkness and cut off from the rest of the world for the next 6 months. The team of scientists who had so bravely manned the telescope were now its winter overcrew custodians of the most critical and remote piece of the puzzle. Their petabyte of data, the key to the EHT's high-resolution vision, was stranded with them on the ice. While the other hard drives were converging on the processing centres in the Northern Hemisphere, the South Pole data sat in its crate waiting. The entire project, the fate of the first black hole image, was held hostage by the Antarctic winter. The tension was unbearable. They had faced down technical glitches and unpredictable weather. They had synchronized a planet. Now all they could do was wait for the Earth to tilt back on its axis and for spring to return to its southernmost point. As the first batches of drives began to arrive at Haystack and Bonn, the initial tentative steps of data analysis could begin. This was not the moment of image creation. That process would take years of work by multiple independent teams, a grueling marathon of calibration and algorithmic reconstruction. This was something much more fundamental, a quick but vital test to answer a single terrifying question. Did we actually get anything? Was there a coherent signal buried in the noise at all, or had they spent years of their lives and a fortune in resources capturing nothing but meaningless static? The technique they used is called forming fringes. You take the data streams from just 2 telescopes, say the one in Arizona and the one in Spain, and you combine them in the correlator, the specialized supercomputer designed for this task. You're asking the machine to look for correlations for any sign that the radio waves arriving at these two disparate locations were part of the same original wavefront from the distant galaxy. If the atomic clocks worked, if the telescopes pointed correctly, if the atmosphere didn't hopelessly scramble the signal, you should see a fringe, a clear oscillating wave pattern. It's the scientific equivalent of hearing a faint pure tone emerge from a blast of static. It's not the song, it's not even the melody, but it is the first confirmation that music is there to be found. The team gathered, their faces illuminated by the glow of a computer monitor. The correlator began its work sifting through the terabytes, comparing the digital ghosts of photons that had travelled for 55 million years, only to land on opposite sides of the planet. The screen was awash of noise. For long, agonizing seconds, nothing appeared. The room was silent, the only sound the hum of the servers. The possibility of complete failure, a prospect too dreadful to voice, hung in the air. Had a subtle error in timing a miscalculation in the complex path of the signals through the atmosphere smeared everything into uselessness. And then it appeared. A faint but unmistakable sine wave bloomed on the screen. A perfect rhythmic pulse. Fringes. A wave of relief so profound it was almost dizzying washed over the team. Cheers erupted. They had it. They had a detection. The planet-sized telescope had worked. The faint whisper from the edge of the event horizon had been caught. The signal was real. This was a monumental victory, the culmination of the entire observing campaign, proof that their audacious gamble had paid off. They had successfully built a telescope the size of Earth and used it to detect a coherent signal from the immediate environment of a supermassive black hole. But as the initial euphoria subsided, a new, more daunting reality began to set in. The fringe was a confirmation, but it was not the prize. It was a single pixel of information, a crude dot in what needed to be a complete picture. Contained within those petabytes of stored data, within the complex interplay of signals from all 8 telescopes, was something more. Hidden in the subtle variations of timing and amplitude in the intricate dance of interference patterns was the information needed to reconstruct an actual image. The shadow was there, they knew it now. But it was still a ghost, shrouded in a storm of noise and distortion. They had successfully collected the raw ingredients. The great challenge now was to turn this mountain of abstract data, these numbers stored on thousands of hard drives, into a portrait of the invisible. The real work, the painstaking process of decoding the universe's most extreme message, was only just beginning. The silent click of a shutter multiplied by 8 and spread across a planet had finally ceased. For days, the Event Horizon telescope had stared unblinking into the heart of the Virgo galaxy cluster, drinking in the faint ancient light from the edge of reality. The observation was a masterpiece of global coordination, a testament to human ambition. But as the great dishes turned away from Messier 87, the most treacherous part of the journey was only just beginning. The discovery wasn't in the observing, it was in the decoding. The truth wasn't captured in the telescopes, it was buried waiting to be exhumed from a digital tomb. The first step was not one of elegant computation, but of brute force logistics. The sheer volume of data, a staggering 5 petabytes, was far too vast to be transmitted over the internet. This was a torrent of information so immense it would have choked the world's digital arteries. And so the project reverted to a method as old as the postal service. Helium-filled hard drives, the precious cargo carrying the faint whispers of M87 synthesis, were carefully packed into climate-controlled cases. They were not just electronics. They were digital fossils holding the encoded imprint of light that had travelled for 55 million years, only to be snagged by our planetary net in its final moments. From the high dry air of the Atacama Desert in Chile, from the volcanic peak of Mauna Kea in Hawaii, from the sun-drenched plains of Spain, and even from the desolate frozen expanse of the South Pole, a fleet of FedEx jets began a global convergence. You can imagine the scientists tracking these shipments with a nervous intensity usually reserved for astronauts on a re-entry trajectory. A single lost crate, a single damaged drive would be catastrophic. It would be like losing a musician from a world-spanning orchestra, leaving a permanent, uncorrectable silence in the final symphony. Each drive held a unique piece of the puzzle, a recording of the universe from a single perspective. Without all of them, the full coherent picture would be impossible. The drives arrived safely converging on two nerve centers of the operation, the MIT Haystack Observatory in Massachusetts and the Max Planck Institute for Radio Astronomy in Bonn, Germany. Here, racks of supercomputers stood ready not to create an image but to perform a task far more fundamental and far more grueling. They had to confront the data itself, and the raw data was a monster. To look at the unfiltered stream of numbers from any single telescope was to see nothing but chaos. It was a howling primordial static, a digital representation of the universe's background noise, punctuated by the faint, almost imperceptible heartbeat of their target. The signal from M87's photon ring was so astonishingly weak, it was like trying to hear a single pin drop in the middle of a hurricane that spans a continent. The sources of this noise were legion each, a formidable obstacle. The most immediate enemy was our own planet's atmosphere. As those precious few radio waves descended towards Earth, they had to fight their way through miles of turbulent air. The primary culprit was water vapor. Every tumbling water molecule in the sky acts like a tiny random lens scattering and delaying the light. This scrambles what's known as the wave's phase, the precise timing of its crests and troughs. For an interferometer that relies on combining waves in perfect synchrony, this is a disaster. It's like trying to judge the exact shape of a pebble thrown into a still pond, but you're forced to view the ripples through a sheet of violently boiling water. The celestial wavefront, so pure and coherent across millions of light years, was being shattered into a distorted, unrecognizable mess in the last few microseconds of its journey. Then came the instrumental noise. Each of the 8 telescopes was a unique individual, a complex symphony of steel electronics and cryogenics. Each had its own personality, its own subtle hums, crackles, and electronic quirks that were unavoidably imprinted onto the data. These were artifacts ghosts in the machine that had nothing to do with the black hole, but were screaming at the same volume as the signal itself, and beneath it all was the tyranny of time. The entire experiment hinged on atomic clocks' miracles of stability that lose only a second every 100 million years. But over the vast distances of the EHT from Hawaii to Spain, even that near-perfect precision wasn't enough. An error of just a trillionth of a second, a picosecond in clock synchronization, would be enough to completely dephase the signals, wiping the cosmic slate clean. The data from one telescope would drift out of time with another, and the precious interference pattern they were looking for would be lost forever, dissolved back into the meaningless static. Before any picture could be contemplated, this mountain of noise had to be leveled. This was the stage of calibration, the first great intellectual sieve through which the data must pass. It was a painstaking, methodical process of digital hygiene, of cleaning the cosmic crime scene to isolate the faintest of fingerprints. The team couldn't remove the atmospheric distortion directly from the M87 key data, because they didn't yet know what the signal was supposed to look like, so they used a clever trick. Periodically, during the observations, all the telescopes would pivot away from M87 Kun to look at a nearby quasar. These quasars are intensely bright, distant, and most importantly structurally simple. For the EHT's purposes, they are just unresolved points of light. They are predictable, well-understood celestial lighthouses. By looking at these calibrators, the scientists could see exactly what the atmosphere and the instruments were doing to a known signal at that specific moment in time. They could map the distortion, creating a dynamic second-by-second correction key for each and every telescope in the array. It was the equivalent of a global orchestra tuning itself. Before attempting the complex symphony of the black hole, all the instruments first played a simple common note, the quasar, allowing the conductor to identify which instruments were sharp, which were flat, and which were being distorted by the acoustics of their particular location. This calibration data was the key that would unlock everything, allowing them to mathematically subtract the Earth's chaos from the celestial message. With the data cleaned and the clocks aligned with breathtaking precision, the real computational heavy lifting could begin at the correlators. These were not imagers, they were matchmakers. The supercomputers ingested the calibrated data streams from every possible pair of telescopes, ALMA and the LMT, JCMT and the SPT, and so on. For each pair, the computer performed a single monumental task: it searched for the signal. It digitally slid one telescope's data stream back and forth against the other's, searching through trillions of possibilities for the exact moment of overlap, the precise picosecond alignment, where the two independent recordings of the same cosmic wavefront would snap into perfect synchronization. This process is called fringe fitting, and when the computer finds a match, the two signals interfere, creating a characteristic wave pattern, a fringe. Finding that fringe is a moment of pure scientific triumph. It is the first definitive proof that two telescopes separated by thousands of miles have successfully captured the very same photon. It is the sound of two distinct voices in a global choir hitting the exact same note at the exact same time. Each successful correlation produces not a pixel of an image, but something far more abstract, a single data point called a visibility. This visibility contains a tiny fragment of information, a measurement of the brightness and structure of the black hole's image on a specific scale, corresponding to the distance between the two telescopes that made the measurement. One baseline, one visibility. Over the course of the night, as the Earth turned, the distances and orientations between the telescopes constantly changed, allowing them to measure thousands of these visibilities, each one a new, unique clue. After months of this Herculean computational effort, the team had its prize, a dataset of visibilities. But here they faced a new and profound challenge, perhaps the most daunting of all. They had conquered the noise, they had synchronized a planet, and they had found the signal, but they still did not have a picture, not even close. What they had was a list of numbers, a sparse and incomplete set of clues. To understand the problem, you have to think about what an image truly is. Any image can be deconstructed into a combination of simple patterns, like breaking down a complex musical chord into its individual frequencies. The EHT, because it is an interferometer made of only 8 telescopes, doesn't see the image directly. Instead, it samples some of these underlying patterns or spatial frequencies. The farther apart the telescopes, the finer the details they can measure. Imagine trying to perfectly reconstruct a human face when you're only allowed to see it through a dozen tiny scattered pinholes in a screen. You might see the glint of an eye through one, a piece of a smile through another, the curve of a cheek through a third. Your brain would try to fill in the gaps based on your experience of what faces look like. The EHT data was precisely this, a collection of tantalizing but woefully incomplete glimpses. The Earth's rotation helped immensely, sweeping the telescope baselines across the sky and allowing them to sample more frequencies, a technique called aperture synthesis. But even with this, the gaps in the data were enormous. They had a few notes from the symphony, but they needed to reconstruct the entire score. Mathematically, this is what's known as an ill-posed problem. For any sparse set of data, there are literally infinite possible images that could in theory produce it. A single point of light could produce their data. A picture of a cat could be contorted to fit their data. How could they possibly find the one true image of the black hole from this infinity of possibilities? The answer could no longer come from the hardware or the raw signal. It had to come from human ingenuity, from logic, and from the creation of powerful new algorithms designed to navigate this vast ocean of uncertainty. The data provided the constraints, the rigid guardrails, but software would have to paint the picture. This gave rise to a new phase of the project, a quiet, intense battle waged in lines of code and computational theory. The collaboration had developed several different imaging algorithms, each one representing a different philosophical approach to solving the puzzle of the missing information. These algorithms were not simple tools, they were complex inference engines. They worked by creating a trial image, calculating what visibilities that image would have produced, and comparing it to the real EHT data. Then they would subtly change the image and check again, iterating millions of times, slowly morphing the image until it converged on a solution that both fit the data perfectly and obeyed certain fundamental rules. These rules, or priors, were the algorithm's secret weapon. They were assumptions based on our knowledge of physics and the nature of real-world images. For instance, an image cannot have negative brightness. It shouldn't have impossibly sharp, single-pixel changes in brightness. It should be somewhat smooth. The different imaging pipelines were distinguished by the priors they favoured. One of the main techniques, called chirp, acted like a meticulous artist. It assumed that the image should be smooth and that neighbouring patches of the image should look similar, a powerful prior that discourages noisy, nonsensical solutions. Another Samaeli behaved more like a minimalist sculptor. It operated on the principle of Occam's razor, seeking the absolute simplest image, the one with the fewest features, and the most black space that could still perfectly explain the data. It strove to carve away everything that was not explicitly demanded by the observations, producing beautifully clean and conservative results. These different algorithmic philosophies were essential. They were different ways of asking the universe the same question. And this led to the final and perhaps most crucial safeguard of the entire endeavour. It was a safeguard not against atmospheric noise or clock errors, but against the scientists themselves. The team was acutely aware of the greatest trap in science, confirmation bias. They knew what Einstein's theories predicted: they should find a ring of a certain size of shadow in the middle. The human mind is a masterful pattern recognition machine, but it is also dangerously good at finding the patterns it wants to find. What if subconsciously a scientist tweaked their algorithm just so choosing the parameters that nudged their final image closer to the expected theoretical result? Such a mistake could undermine the credibility of the entire multi-decade billion-dollar project. The result had to be unimpeachably objective. To ensure this, the collaboration's leadership enacted a protocol of extraordinary rigour. They divided the imaging specialists into 4 separate independent teams. Each team was given the exact same calibrated visibility data, the final product from the correlators. But from that point on, they were placed in a state of strict scientific quarantine. They were forbidden from speaking to one another. They had to work in complete isolation, each team sequestered in its own intellectual silo. They were encouraged to use different algorithms and different imaging parameters to attack the problem from their own unique direction. The team from Harvard might favour one approach while the team from Arizona favoured another. No one knew what the other teams were seeing. No one knew if their burgeoning image of a glowing ring was a genuine feature of the universe or a phantom and artifact of their own chosen software. For months, these 4 teams worked in parallel, each staring at their own screens, coaxing a picture of reality out of the sparse data. The tension was immense. The entire legacy of the Event Horizon Telescope rested on the outcome of this blind test. If the 4 teams produced 4 wildly different images, one a blob, one a crescent, one a double jet, it would mean the data was too sparse, the problem too ill-posed. The result would be a noble failure, a statement that they had reached for something just beyond their grasp. But if these teams working in isolation with different methods and different assumptions all converged on the same fundamental structure, if from the same set of scattered clues 4 different detectives all named the same suspect, it would be the most powerful confirmation imaginable. It would be evidence hammered into bedrock, a discovery not just seen but cross-examined and verified. The algorithms had finished their work. 4 final images now existed, stored on 4 different hard drives, ready for the moment of truth. The scientific quarantine was about to be lifted, and so the great silence ended. For 2 years, the teams had laboured in self-imposed exile, locked away in their own computational fortresses. They were custodians of a ghost, a spectre captured in petabytes of data, a whisper from the edge of space-time 55 million light-years away. Within the coded quiet of their digital monasteries, 4 independent groups of scientists at Harvard, at the Max Planck Institute, at MIT's Haystack Observatory, and in Japan had been given the exact same raw, uncalibrated information from the Event Horizon Telescope. It was a planetary puzzle box, and each team held an identical scrambled copy. The rules of this extraordinary game were absolute, designed to fend off the most insidious enemy of discovery, ourselves. They were forbidden from communicating their progress, from sharing a single hint of what their nascent images might look like. Human brains are pattern-matching machines wired to find faces in clouds and meaning in noise. If one team caught even a whisper of another's findings, the subtle unconscious desire to conform could corrupt the entire experiment, turning a search for objective truth into a self-fulfilling prophecy. This was their sworn pact, a vow of analytical purity. Each algorithm, each line of code had to be a unique key forged in isolation to unlock the same cosmic vault. If the universe was truly speaking to them, it had to speak the same language to everyone independently. Now, the work was done. The computational engines, having churned through numbers for months on end, finally fell quiet. The digital sieves had sifted every last grain of data. Within their firewalled servers, Each team now possessed a final product, a single painstakingly reconstructed image, a picture of what might be lurking in the heart of the galaxy Messier 87. They held their breath, carrying this fragile monumental secret. Was it a featureless smear of cosmic static, a bizarre unpredicted artifact of their own software, or was it what they had all dared to dream of, the very thing that drove this colossal endeavour? Was it the abyss itself wearing a crown of light? The time had come to break the seals, to bring their separate truths into a single room, and see if they formed a unified reality. The location for this scientific reckoning was the Black Hole Initiative at Harvard University. There was a palpable tension in the air, thick with the accumulated weight of years of hope, frustration, and sheer intellectual toil. It was more than a meeting. It was a kind of trial where the universe itself was both witness and judge. The scientists, who had become intimately familiar with every byte of their own data, were now complete strangers to the results of their colleagues sitting just feet away. One by one, they prepared to reveal their work. Imagine the scene, the hushed conference room, the faint hum of a projector, the faces of brilliant people etched with exhaustion and profound anticipation. This was not a moment for grand speeches. It was a moment of stark, terrifying vulnerability. The first team put their image on the screen. A collective audible gasp filled the room. There, floating in the digital void, was a ring, a lopsided blazing circlet of light brighter on one side than the other, encircling a pit of perfect darkness. It was incredible, a celestial smoke ring blown from the furnace of a galactic core. It was exactly what theory predicted. But this was only one key turning in one lock. Was it a fluke? A stunning, beautiful coincidence born from a single team's specific set of assumptions and code. The relief in the room was instantly replaced by an even greater suspense. The second team stepped forward. Their methodology was different, their imaging software built on entirely different principles. They loaded their file. The screen blinked and a new image appeared. It was the same ring, the same dark center, the same asymmetric glow. It was like looking at two different portraits of the same person, painted by different masters in different styles, yet capturing the identical, unmistakable soul. A wave of laughter and astonished chatter broke the tension, a release of pressure that had been building for years. Then came the third team. Their approach was different still, using another suite of sophisticated algorithms to navigate the treacherous data. Their result flashed onto the screen. Again the ring, a third independent vote from the cosmos confirming the same impossible structure. When the fourth and final team presented their image, it was no longer a moment of suspense, but one of triumphant, almost sacred affirmation. 4 separate paths, beginning from the same chaotic storm of raw radio signals, had all converged on this one unambiguous answer. They had all stared into the heart of M87, and the heart of M87 had stared back with the same unblinking, fiery eye. Tears welled in the eyes of scientists who had dedicated their entire careers to this quest. The emotional impact was overwhelming. This wasn't just data on a screen. It was the culmination of a century of physics, from Einstein's solitary musings to the coordinated dance of 8 observatories and hundreds of brilliant minds. It was a message in a bottle, not from a distant shore, but from a place where space and time themselves come to an end. They had done it. They had built a virtual telescope as wide as the Earth, and it had worked. What they were looking at was not, of course, the black hole itself. A black hole by its very nature is the definition of invisible. What they had captured was its shadow. Think of it this way: you cannot see a hole in the ground in absolute darkness, but if you shine a brilliant light behind it, you see its silhouette perfectly. In the center of M87, the light behind the hole, is a swirling chaotic maelstrom of gas and plasma, the accretion disk. This material, trapped by the black hole's immense gravity, is accelerated to nearly the speed of light, heated to billions of degrees, until it glows with unimaginable ferocity. It is a celestial blowtorch, a source of light so powerful it illuminates the very fabric of space-time. The black hole sitting in the middle of this inferno carves out a sphere of darkness. This shadow is created by the event horizon, the point of no return. Any light from the accretion disk that strays too close that passes within this critical boundary is captured forever, its journey terminated in the singularity. The shadow we see is therefore a direct imprint of the event horizon, an actual silhouette of the edge of reality magnified by the black hole's own gravity, a phenomenon known as gravitational lensing. The math predicted the shadow should be about 2.5 times larger than the event horizon itself, and the size of the shadow on their screens matched the predictions for a black hole of 6.5 billion solar masses with breathtaking precision. But the image revealed something even more profound, even more delicate than the shadow alone. That incandescent circle of light wasn't just the accretion disk glowing behind the black hole. It was something far more exotic. It was the photon ring. This is the last possible place where light can orbit a black hole. Imagine a photon, a single particle of light grazing the edge of the event horizon. If it's too far out, it escapes. If it's too far in, it's captured. But if it hits a razor-thin region known as the photon sphere, it can be forced into a temporary unstable orbit circling the abyss like a moth around a cosmic flame. Light here can loop around the black hole once, twice, 100 times before being flung out in a random direction. What we see in that bright ring is the collective glow of these captured photons, light from all angles, from the front of the disk, the back, the top, the bottom, all gravitationally lensed and focused into a single sharp, luminous loop. It is Einstein's universe in its most extreme and elegant form. The image was a direct visualization of warped space-time, a map of gravity's funhouse sketched in fire. The distinct brightness on one side of the ring was another spectacular confirmation. It was the signature of the black hole's rotation. The material in the accretion disk spinning towards us is boosted in brightness by the Doppler effect, its light waves compressed and intensified. The material spinning away is dimmed. This asymmetry wasn't just a beautiful detail, it was a cosmic speedometer telling the scientists that M87 was spinning, dragging the very fabric of space-time around with it, like a submerged, rotating cannonball dragging water. With 4 consistent images, the next phase of work began a meticulous, almost fanatical process of cross-validation. This was where art met unforgiving statistics. The collaboration now broke their vow of silence and merged their efforts, their goal, no longer to produce an image, but to prove its reality beyond any shadow of a doubt. They began by layering the images on top of one another. The rings aligned with uncanny accuracy. They developed sophisticated metrics to quantify the ringness of the images to statistically measure the presence of a bright ring surrounding a dark central depression. They subjected their findings to every conceivable test, attempting to break them to prove them false. They created vast libraries of synthetic data, simulated universes, where there was no black hole, just a messy jet or a featureless blob of gas, and ran them through the same imaging pipelines. In every single case, their algorithms correctly reported that no ring existed. Then they fed the pipelines synthetic data that did contain a black hole shadow. The software consistently spat out a ring just like the one they saw in the real M87 data. It was a rigorous systematic process of elimination. They were ruling out every other possibility, no matter how remote, leaving only one extraordinary conclusion standing. The teams also had to be sure the features were persistent, that they weren't just a fleeting artifact from a single day's observation. They divided the week of 2017 observational data into different nights. They produced an image from the data taken on April 5th, then another from April 6th, another from April 10th, and one from April 11th. While the turbulent boiling gas of the accretion disk changed from night to night, causing subtle variations in the ring's brightness, the 2 fundamental features remained stubbornly constant: the size of the shadow and its circular shape. This was the gravitational bedrock beneath the shifting sands of astrophysics. The black hole's mass and the laws of general relativity were the cosmic anchor, holding the structure in place day after day. The statistical certainty grew with each test moving into that hallowed ground of scientific discovery known as 5 sigma. This is the gold standard, a declaration that the probability of the result being a random statistical fluke is less than 1 in 3.5 million. The ring was as real as the moons of Jupiter or the mountains on Mars. It was a permanent feature of the cosmos, and for the first time in history we had the eyes to see it. For the next year, the Event Horizon Telescope collaboration held onto the most profound secret in modern astronomy. They prepared 6 monolithic papers detailing every aspect of their monumental effort: the observations, the calibration, the imaging methods, the physical interpretation. The results were peer-reviewed with unprecedented scrutiny. This discovery was going to be written into the history books, and it had to be flawless. As the date for the public announcement approached April 10, 2019, the team planned a global event befitting the discovery. 6 simultaneous press conferences were scheduled in major cities across the world, from Washington, D.C. to Santiago, from Brussels to Tokyo. They knew that what they were about to reveal would transcend the world of science. It would become a cultural touchstone, a new icon for humanity's quest to understand the universe. It was the modern equivalent of Galileo revealing the faces of Venus or Hubble, displaying the vast expanse of galaxies beyond our own. On that fateful morning, the world's media gathered. The scientists, the same ones who'd huddled in that small room at Harvard, now stood on brightly lit stages ready to share their secret with 7 billion people. And then it happened. On giant screens across the planet, the image appeared. A perfect, imperfect circle of fuzzy orange light surrounding a deep, absorbing blackness. It was at once beautiful and terrifying. It looked ancient, primal. There was no caption needed. Everyone everywhere knew exactly what they were looking at. For the first time, we were all together staring into the abyss. It was the face of gravity itself. The ghost in the machine of the universe had finally been caught on camera. This single image was a triumph on so many levels. It was a staggering technological achievement, the product of a global collaboration that had synchronized atomic clocks and hard drives across continents. It was a profound confirmation of a theory devised a century ago by a lone genius who never dreamed we could actually photograph his thought experiment. But most of all, it was a moment of pure exploration. We had journeyed to the edge of an object from which not even light can escape, and we had returned with a picture. Yet like all great discoveries, this image answered one profound question, while opening a floodgate of new ones. This was not an endpoint. It was a key unlocking an entirely new laboratory, the most extreme laboratory in the cosmos. Now that we could see the unseeable, what other secrets were hiding within that fiery gravitational halo? What new physics was waiting to be found at the event horizon? And so, we are left here in the quiet afterglow of revelation. That ring of fire now etched into our collective consciousness is so much more than an image. It is a destination reached after a century of wandering through the strange and beautiful wilderness of Einstein's imagination. For generations, this object was a ghost, a mathematical spectre haunting the equations of general relativity. It was a point of infinite density, a rupture in the fabric of reality, a place from which nothing, not even light, could escape. We gave it a name, a black hole, a fittingly absolute label for something so profoundly unknowable. It was the ultimate monster in the cosmic dark, defined only by its absence, by the perfect and terrifying silence it imposed on the universe around it. We inferred its presence through the graceful waltz of orbiting stars or the violent death cries of matter spiraling to its doom. But we had never truly seen it. We had never stared into the abyss and seen the abyss stare back, until now. What the Event Horizon Telescope delivered was not an artist's impression, not a simulation, but a direct photon-by-photon transcription of gravity's most extreme masterpiece. That single snapshot, assembled from a petabyte of data, from a chorus of radio dishes scattered across our world, transformed the black hole from a concept into a place. It gave a face to the monster, and in doing so revealed it not as a monster at all, but as a fundamental, breathtaking feature of our cosmic architecture. The journey to this image was a pilgrimage of the human mind. It began with a thought experiment with ink on paper, and ended with an Earth-sized telescope capturing the faint ancient light from the edge of oblivion, a signal that had travelled for 55 million years just to greet us. This achievement was not merely the closing of a chapter, it was the inauguration of an entirely new era. We have now entered the age of observational black hole astronomy. The theoretical beast has been brought into the empirical fold, ready for interrogation, for measurement, for understanding. We are no longer limited to tracking shadows. We can now study the light that defines them, and that light speaks volumes. Within that shimmering, lopsided donut of plasma, we can finally read the vital statistics of this cosmic titan. The diameter of that dark central region, the black hole's shadow, is a direct ruler for the event horizon itself, and from its size we can weigh the giant. The number it returned is almost incomprehensibly vast, 6.5 billion times the mass of our own Sun. Imagine if you can compressing 6.5 billion of our stars with all their light, their heat, their planetary systems into a volume of space not much larger than our solar system. That is the scale of the gravitational sovereign reigning over the M87 galaxy. Its sheer mass dictates the orbits of hundreds of billions of stars, shaping the very structure and destiny of its galactic home. The image provides a stunning confirmation of this mass, a figure that astronomers had estimated through other means, but which we now see written in the geometry of space-time itself. But the image tells us more than just its weight. Look closer at the ring. Notice how it isn't uniform. The southern half of the ring is intensely brilliantly bright, while the northern part is dimmer, more subdued. This asymmetry is not an accident or a flaw in the image. It is the unmistakable signature of the black hole's spin. The material orbiting the black hole is moving at relativistic speeds, a significant fraction of the speed of light. The gas on the side of the disk rotating towards us appears brighter, its light amplified and blue shifted by an effect known as Doppler beaming. The gas rotating away from us is consequently dimmed. This simple variance in brightness is a cosmic speedometer, and it tells us unequivocally that M87 is spinning. It's a gravitational gyroscope, a monolithic vortex of space-time twisting the universe around it as it rotates. And we can even discern the direction of that rotation. It is spinning clockwise with its axis pointed slightly away from our line of sight. This revelation that the black hole spins is the key to understanding its most ferocious feature, the colossal, relativistic jet that erupts from its core. For decades we've observed this celestial blowtorch, a focused beam of particles and energy, 5,000 light-years long, blasting out of M87's centre at nearly the speed of light. How could a creature that only consumes, that only pulls inward power, the most energetic, outward-bound phenomenon in its galaxy? The answer lies in the spin we now see confirmed in the EHT image. A spinning black hole doesn't just warp space, it drags space along with it. This effect, called frame dragging, creates a violent swirling ergosphere just outside the event horizon, a region of no return for space-time itself. Magnetic field lines anchored in the swirling accretion disk are caught in this cosmic blender. They are twisted into a tightly wound, immensely powerful coil, a kind of galactic superconductor. Through a process known as the Blandford-Znajek mechanism, the rotational energy of the black hole itself is extracted along these magnetic field lines. The black hole becomes a cosmic dynamo of unimaginable power, converting its own angular momentum into a directed blast of kinetic energy. The image of the spinning ring is therefore not just a portrait of the black hole's maw, but a glimpse of the engine that drives its magnificent galaxy-shaping jets. We are witnessing for the first time the base of the cosmic cannon. With such profound insights gleaned from a single static image, the question that now electrifies the entire astronomical community is what comes next. The success with M87 was not an end goal but a proof of concept. The Event Horizon Telescope was built for a dual purpose, and its other primary target lies much closer to home. We now turn our planet-sized eye towards the heart of our very own galaxy, the Milky Way, towards the supermassive black hole known as Sagittarius A. Our black hole is a very different beast from M87Q. It is a relative lightweight, a mere 4 million solar masses, over 1,000 times less massive than its distant cousin. This smaller size presents a formidable new challenge. Because it is smaller, the gas in its accretion disk orbits much faster. While matter takes days or weeks to circle M87, it completes an orbit around Sagittarius Alpha in a matter of minutes. Observing it is like trying to take a crystal-clear, long-exposure photograph of a hummingbird's wings. The image changes faster than our telescope can capture it. Furthermore, our view is obscured by the gas and dust of the galactic plane, a cosmic fog that scatters the radio waves we need to detect. Yet the rewards for overcoming these hurdles are immeasurable. To image Sagittarius A is to see the gravitational anchor of our own cosmic home. It is to directly visualize the object whose gravity orchestrates the dance of our sun and all the stars you see in the night sky. It will provide a critical second data point, allowing us to test if the laws of gravity described by Einstein hold true for black holes of vastly different scales. Does a black hole 1,000th the mass still cast a perfectly circular shadow? Does its light ring behave in precisely the way the theory predicts? Every new black hole we image becomes another rigorous test for general relativity in Sagittarius. A is the most important test subject of all. But the ambition of the EHT collaboration extends far beyond a second photograph. The ultimate goal is to move from still life portraits to cinema. The next generation of the Event Horizon telescope is already being planned. It involves adding more telescopes to the array both on the ground and one day in space, increasing its resolution and its sensitivity. With this enhanced power, we can take snapshots more frequently, stringing them together to create the first ever time-lapse movies of a black hole's immediate environment. Imagine what we will see. We will witness the turbulent, chaotic ballet of plasma in the accretion disk, watching hot spots flare up and die down as they orbit the abyss. We could see a star wandering too close being shredded by tidal forces, its matter pulled into a luminous, screaming ribbon of gas before being consumed. We might watch in near real time the very process by which the jet is launched, seeing the magnetic fields coil and erupt from the black hole's poles. We would no longer be studying a static phenomenon but a living, breathing dynamic engine of cosmic consequence. These movies would allow us to probe the physics of accretion and ejection in a way that is simply impossible with any other tool. They would be our ultimate laboratory for studying matter under the most extreme conditions of temperature, pressure, and gravity that the universe can conjure. And with every frame of these future films, with every new pixel of data, we will be pushing Einstein's theory closer to its breaking point. General relativity has weathered every storm we have thrown at it, for over a century, passing every test with flawless precision. But we know with absolute certainty that it cannot be the final word. It does not account for the strange rules of quantum mechanics that govern the very small. At the centre of a black hole in the singularity, the immense gravity of the very large meets the infinitesimal scale of the quantum world. Here our two great pillars of modern physics crumble, producing nonsensical answers of infinite density and temperature. To resolve this paradox, we need a new theory, a theory of quantum gravity, a theory of everything that can unite these two disparate domains. That new theory might predict subtle deviations from general relativity in the regions of most extreme gravity. Perhaps the shadow of a black hole isn't perfectly circular. Perhaps its size deviates by a fraction of a percent from Einstein's prediction. Finding such a deviation would be the most profound discovery of the 21st century. It would be the first crack in the edifice of general relativity, a crack through which we could glimpse the new physics that lies beyond. The Event Horizon telescope, by measuring the size and shape of black hole shadows with ever-increasing precision, is our best hope for finding that first crucial clue. It is a machine built not just to confirm a century-old theory, but to hunt for the evidence that will one day supplant it. In the end, when we look back at that iconic image of M87, we see more than the triumph of a scientific theory. We see the triumph of the human spirit. This was an achievement born not of a single nation or a single mind, but of a global symphony of collaboration. Over 200 scientists and engineers from 20 countries and 60 institutions, speaking dozens of languages, set aside their differences. They united with a singular, audacious purpose to build a telescope as large as the Earth itself. They synchronized atomic clocks with nanosecond precision, flew hard drives across continents, and wrote millions of lines of code to weave a faint whispering signal into a coherent portrait of a distant universe. It is a testament to what we as a species can accomplish when we are driven by curiosity, when we work together, and when we dare to ask the biggest questions. Why are we here? What are the fundamental laws that govern our universe, and what lies out there in the deepest, darkest corners of the cosmos? The quest to see the unseeable, to know the unknowable, is coded into our DNA. It is the same impulse that drove our ancestors to look up at the stars and trace pictures in the constellations. It is the same fire that propelled explorers across unknown oceans and that lifted us from the bonds of our own world to walk upon another. The black hole at the heart of M87 lay waiting in the darkness for millions of years, a silent testament to the power of gravity. And here on Earth, a fragile species on a tiny speck of rock looked up and wondered. And through sheer ingenuity, persistence, and a boundless desire to understand, we built an eye large enough to see it. That ring of light is not just a picture of a black hole. It is a self-portrait of humanity at its very best, a declaration that no mystery is too profound, and no distance is too great for the reach of the human mind.